In this lecture, we will be looking at another method to investigate reaction mechanisms, and in particular, the rate determining step of a reaction. You may recall that the rate determining step is the slowest step of the reaction, the step that has the highest activation energy barrier, hence the slowest step, and the other steps of the reaction mechanisms are basically the fast step. The reason why the rate determining step, or RDS, is very important because that step will dictate the overall rate of the reaction. So we will look at another type experiment or study called Kinetic Isotope Effects Studies, or KIE. So in this presentation, we will look at first a definition of kinetic isotope effect. Then we'll break it down into two types, primary, and we'll also look at the secondary, and we'll utilize these techniques or experimental results to assist in the determination of reaction mechanisms. So let's begin. For some reactions, such as the one shown below, it is obvious that substituting a isotope for another one, or a regular atom for an isotope, alters the rate of the reaction. So let's look at this elimination reaction here. This is an elimination reaction in which we have a strong base here, and we have hydrogens here which can act as protons, and a good leaving group here. So as you know from your general organic chemistry course, this is a classic elimination reaction in which the base abstracts this hydrogen. This is a good leaving group to form a double bond here. Notice it could not be formed on the other end because this is an sp2 carbon to the phenyl ring. The main aspect here, though, is for the molecule that has hydrogens, the rate is relative rate is 4.6. For the molecule that has deuterium in the same positions, measuring the rate, its rate is much slower, 1.1. So bottom line is, it appears that whenever we have hydrogen as part of the reactant, its rate is faster than a substitution with deuterium. Such studies are known as kinetic isotope effect studies. As you can imagine, kinetic rates, isotope because we're substituting a hydrogen for deuterium, or one for the other, and of course the effects on the overall rate of the reaction. And as we'll see in a second, it's really affecting the rates of the RDS in the reaction mechanism. So let's see if we can utilize this information. So a possible mechanism, stepwise mechanism that we have seen from our general organic chemistry course, is that the base abstracts this hydrogen here to put 2 electrons here, and that could be the rate determining step. And of course, in a fast step, we have the elimination. This type mechanism we'll see later on is called the elimination conjugate base, because here's a conjugate base. The one that we're more familiar with in organic chemistry is concerted, where this occurs in one step. the H is eliminated, and the trimethyl ammonium species leaves as the leaving group, concerted. But the bottom line is, in that most important step, a CH bond is broken. Okay, for the second reaction, here we have a CD bond that is now broken. So the question is, if this is the rate determining step which dictates the overall rate of the reaction, why is this faster than this one? Let's see why. It is obvious from the previous mechanism that a CH and a CD bond, one was broken. So it would imply that the energy requirement to break a CH bond and a CH bond, those energies are different. In other words, one bond seems to be stronger than the other bond. Let's look at the dissociation energies for these CH and CD bonds. For the CD bond, the dissociation energy is 341.4 kilojoules per mole, and to break a CH bond, it is 338 kilojoules per mole. You can see that it requires more energy to break a CD bond compared to a CH bond. That concept is illustrated here, where we have here the CD 0 point energy. What does that mean? As you know, if you have a C and a D, for example, this bond is constantly vibrating. Let's make that 4 bonds. So this bond here for the carbon to deuterium is constantly vibrating. So the frequency, which is the minimum energy, called the 0 point energy, is here. If we have a CH bond, the same thing happens. The minimum energy, called the 0 point energy, for that vibration is higher. And that has to do with the difference in atomic weights for CD versus CH. So you may want to refresh your memory in terms of the energy requirements based on the reduced mass, or the mass of the atoms involved. I think you can look at Hooke's law to refresh your memory with that. Bottom line is, anyhow, the energy required to go from the 0 point energy for CD to breakage is requires more energy than going from the CH bond, from the 0 point energy, to bond dissociation or breakage. So less energy. So you can see where we're going with this. If there's less energy required for bond breakage, the energy of activation for this bond breakage is lower, hence faster reaction, compared to CD, which requires more energy for bond breakage, and of course here that would be a slower reaction. So let's apply that here. So in the rate determining step here, as you can see, this is a bond breakage right here to give this conjugate base. This is here the rate determining step. This is a weaker bond than this bond here. So therefore this is a slower reaction for the rate determining step for this reaction here compared to this reaction here, which is faster because this bond energy here is less than this. So since we're looking at the rate determining step, which determines the overall rate of the reaction, now we can see why this is a faster reaction than this one, which is shown on the next slide, which is a faster reaction than this one. Okay, so let's see if we can apply that concept over here to another type reaction. So for the base catalyzed rearrangement, notice this is a rearrangement reaction. The KIE, or the kinetic isotope effect studies, KH over KD, notice KH is for the CH bond, KD is for the CD bond, is 7.76. As you can see, that's a very large number, and typically kinetic isotope effects are pretty large if we have CH versus CD. Why? Because of the differences in mass between hydrogen and deuterium. As you know from Gen Chem, deuterium is twice as heavy as hydrogen. So you would expect the rate determining step for the CH bond breakage to be much larger than that for the CD bond breakage. So the kinetic isotope effect is pretty large for CH bond breakage here. By the way, I should point out that this type kinetic isotope effect is known as the primary kinetic isotope effect, or written here as 1 superscript 0, primary isotope effect. As you know, in chemistry we have lots of abbreviations to represent different concepts. So this is a primary isotope effect where there is a CH or a CD bond breakage. To be more general, it's just a bond breakage, because we will see later on it's possible to have a carbon-carbon bond breakage. Anyhow, for this reaction, the kinetic isotope effect is 7.76. So the question that we have now is, can we use this information here to determine the rate determining step and to propose a reasonable mechanism for this reaction? So here is the carbon in this experiment. It was synthesized, this molecule was synthesized where one molecule was H and the reaction rate measured, and the other molecule is where this is deuterium and the rate measured. So you can imagine it's a very time consuming experiment to make these different molecules with a hydrogen and deuterium, and then measuring the rates of these reactions. So let's see if we can utilize that information to deduce a rate determining step and reaction mechanism. So since it's a primary kinetic isotope effect, it implies that a bond breakage occurs in the rate determining step. In this case, based on the design of the molecule, it is either a CH or a CD bond that's broken based on which molecule is used. If the molecule is a CH here, you can see this would be the rate determining step to create the anion here, or the conjugate base. And of course, as you can imagine, another molecule is made where this is a CD and the rate measured where the CD bond is now broken to give the same conjugate base. This occurs, of course, in the rate determining step because we observe a difference in rates for the different bond breakage. primary kinetic isotope effect. Once you have this, here are resonance structures. So now we can put the negative charge here, or the unshaped pair of electrons here, which can now abstract a hydrogen from the solvent here, and we get this as our isomerized product. So this would be the mechanism. And most important, or very important, is that this is the rate determining step, and this is the fast step. In your mechanism, you will always propose a rate determining step and fast steps for the reaction. The reason why, again, let me emphasize, because the rate determining step for a reaction dictates the overall rate of that particular reaction. Okay, let's look at another experiment here. And this is for the decarboxylation of a beta keto carboxylic acid. And here it is. It's called a beta because this is the alpha carbon, and this is the beta carbon from the carboxylic acid. So this is a beta keto carboxylic acid. If you should heat this up, you will observe that a reaction occurs where this is lost as carbon dioxide, and this is converted into a ketone here. And this one here is acetophenone. Let's look at this value, however. This is a kinetic isotope effect of 1.04 plus or minus 0.01. I'll emphasize that in a second. But the bottom line is that this is a carbon isotope effect. Notice it's a carbon, which means that it's a carbon-carbon bond that's broken in the rate determining step. Not hydrogen in this case, because it is a carbon primary kinetic isotope effect. Of course, as you can see here, the two isotopes of carbon that were measured would be carbon-12 and carbon-13. They're two isotopes of carbon. Again, just to refresh your memory, the third would be carbon-14. This is carbon-13. These are the two isotopes here. Let's look at the value here. The primary isotope effect for the carbon-carbon bond breakage is 1.04. Very small. And the reason why it's very small is because the difference in the atomic weights of carbon-12 and carbon-13 is very small. Notice for hydrogen, the kinetic isotope effect was very large because the difference between the hydrogen and deuterium atomic mass weight is twice as much. So you'd expect that energy requirement to be very large for that bond breakage. But in this case, it's 13 versus 12, so it's very small. We usually report here a experimental error. That's plus or minus error. Which means that in this experiment, the experimental individual or the experimentalist measured this reaction quite a few times, at least 3, 4, 5 times. And the difference in these measurements were pretty close, just varied by 0.01, which means that this number here is a real number. It is a real number in terms of reflecting the difference in primary kinetic isotope effect for the carbon-carbon isotopes here. So for this experiment here, one of these carbons, more than likely this carbon here, for the first experiment, this was carbon-12, and they measured the rate of this reaction. And in the second reaction, they included carbon-13 here and measured the rate of that reaction. And it turns out to be this in terms of the difference in rates. So the bottom line is a carbon-carbon bond is broken in the rate determining step. Based on the reaction here, it is obvious that this is the bond that's highlighted in red here that's broken in the rate determining step. So let's see if we can come up with a mechanism that is consistent with that experimental observation. Okay, so here we go. So we know that a carbon-carbon bond is broken in the rate determining step. We know this is the product, so more than likely this is the bond that's broken. Here's a possible mechanism. It's concerted. So this bond is broken here. It picks up a hydrogen here, and here's our carbon dioxide right here. Let me just highlight it. Right here is our carbon dioxide, and this bond is broken to give this enol. It's called an enol because it's an ene and an ol. As you know from general organic, the enol is not as stable as the keto form, so there's a tautomerization which gives the keto form from the enol, where we have a carbon-oxygen double bond. So you'd expect this to be a fast step, and it is a fast step. Why? Because it's an equilibrium. And of course, you know, equilibria are extremely fast. It's just a matter of, it can't be measured in terms of rates. It's just the values of the concentration of the reactant and products that determines the equilibrium constant. So bottom line is, we have here a primary kinetic isotope effect. In this case, it's a carbon-carbon bond that's broken. So the measurement here is carbon 12, carbon 13, very small compared to the CH bond breakage in a primary kinetic isotope effect, as we have seen earlier. But this information can still be used to determine the rate determining step of a reaction based on the bond breakage and subsequent steps, which are fairly fast. Okay, let's go on. Let's now look at another concept. This is the secondary kinetic isotope effect, or 2' superscript 0 secondary isotope effect. Let's look at this reaction here. So shown below is the kinetic isotope effect for this reaction. So we have the reactant here going to a product. Let's see if we can see the difference. So here we have a carbon that's bonded to an OH. In the product, it's gone as water, because as you can imagine, there's a protonation here to get a good leaving group, and of course the Cl comes in as the substitution. So you can see that this is a substitution reaction based on the solvent here, HCl, which is a protic compound, more than likely done in water. It is more than likely an SN1 reaction. SN1. Remember, an SN1 reaction we proposed in general organic that an SN1 reaction requires the formation of a carbocation in the rate determining step. But let's see if we can use this isotope effect measurement here to determine what is the mechanism. So here we have a CH. So in the first experiment, you can imagine the experimentalist made this molecule with CH, measured the rate, then went back and made the molecule with CD and measured the rate. And of course, it was observed that the KH, the rate constant for the hydrogen, is a little faster than the K rate for the deuterium substituted molecule, just 1.18. But based on the plus or minus values here, This is a real number, so this is really a rate difference for hydrogen versus the compound that has deuterium. How do we explain this? Let's see if we can explain this. But first of all, notice that this CH bond is still here in the product, which also means that the CD bond is also in the product. Conclusion: the CH bond is not broken in going from reactant here to product, as we have seen before. So it's not a primary kinetic isotope effect, and that's why it's different. This one is called a secondary, and we'll see why in a second. But let's see here how we can explain these results. So what we have here is the vibrational frequency for the CH and the CD bond for the sp3 carbon and sp2 carbon. You may recall that a C, let's just do this, H, if it's sp3, it has 4 bonds to it, and if it's sp2, it has here an H and just 3 bonds to it. Typical sp2 carbon would be your carbocation, as we have seen before. The bottom line is, based on infrared spectroscopy, the vibrational mode here is different from the vibrational mode here. As you can see here, here is the CH 1340, but here's a big difference. In the sp2, it's 800 reciprocal centimeters. Another vibrational mode here doesn't really change a whole lot. You may recall from your infrared spectroscopy that there are many vibrational modes to in any molecule, and as a result to any bond. Difference in vibrational mode. But the key here is, here's a big difference going from the sp3 to the sp2. For the CD, so if this were deuterium here, one of the vibrational modes goes from 957 for the sp3 carbon D bond to 571. A difference, notice, not as huge as this, but a difference here if this were actually deuterium here, as we can see for the D bond. So the bottom line is, there's a vibrational difference in going from sp, let's put this here as sp3 going to sp2, as reflected here. Let's look at that concept differently, and let's use the potential energy diagram here. So here we have the sp3 carbon. For that sp3 carbon to go to the sp2 carbon, as you know, it goes through a transition state here, and here is what it looks like. So as you can see here, the energy difference here for the sp3 going to the sp2 carbon, as reflected from the vibrational mode here. So with that said, what that means is that for this reaction, notice again, there's no bond breakage here in going to the product, but there seems to be a change in hybridization of this carbon in the rate determining step for the reaction mechanism as it goes to the product. Let's see what that could be. So here is an acid and here's a base, so a likely step here is the protonation of this OH, because it's a very poor leaving group, to give that protonation. It's an acid-base equilibrium, very fast. So it's an equilibrium, the rates are not really measured, it's just a concentration of the reactant and the product to give an equilibrium value. So that's fast. So notice this carbon here is still sp3, When this leaves, this carbon is now sp2. A change in hybridization here is reflected if we have a H versus a D in going from an sp3 to an sp2. Okay, notice again that this value here is much smaller than your primary kinetic isotope effect. As we can see from the vibrational mode, we're not breaking a bond this time, but it's just a difference in vibrational mode in going from sp3 to an sp2. One thing I should point out again, that this is plus 1.18. As we'll see in a second, we can have a value that's less than 1, less than unity. But this is greater than 1 unity, so we call this a typical secondary isotope effect. I'm emphasizing that because we'll look at the inverse in a second. So conclusion from the slide. This is a reaction. The reactant here is going to the product. For this reaction here, the CH-CD bond is not broken, but there is a secondary kinetic isotope effect, which means that there is a change in hybridization in the rate determining step for the reaction as it proceeds from reactant to product. And here's the mechanism. This is the sp3 and this is the sp2, and here's your carbocation, and here is the rate determining step, which is consistent with what we have seen in general organic course. And of course the fast step here is where the Cl comes in and bonds here to give the product in a fast step. Okay, let us look at another reaction here, and I want to point out here again that this value here is less than unity, less than 1. So we call this is less than unity, we call this an inverse. So the other one was a normal secondary kinetic isotope effect, greater than unity, and the inverse is less than unity. Of course, you can assume what happens here. For these reactions, the carbon that contains the H and of course the CD, it goes from an sp2 to an sp3 in the rate determining step, and the other steps of course are fast. So let's use that information here to propose a mechanism. Again, since it's less than 1, a carbon is transformed from sp2 to sp3 in the rate determining step and not sp3 to sp2 as we have shown earlier for the SN1 type reaction. So the question now is, can we utilize this information here to propose a mechanism? So let's just refresh how we can use this information. It's a secondary kinetic isotope effect. How do we know that? Because in going from reactant to product, there's no CH-CD bond breakage. Another bit of information from this value is that it's less than 1, which means that's inverse, which means that a carbon sp2 goes to an sp3 in the rate determining step. So let's apply that to a mechanism here. Yeah, well, this gives a graphical illustration of what we just described, and that the energy required for the for the transformation of the hybridized state from the sp2 to the sp3 is less than that here. So that's just a graphical illustration of that concept I just described. But let's apply that here. So here's the reaction again. Inverse isotope effect because this is less than unity. Secondary because the hybridized state here does not, there's no CH bond breakage in going from reactants to product. So therefore it's a secondary KIE. So the mechanism is, here is our sp2 carbon. As you can imagine here, the SCN, which is a nucleophilic reagent, attacks this carbon here, or either one because it's symmetrical, to give this. Notice that now this is sp3. This is sp2 here, and this is sp3. Of course, our analysis could go in the reverse because it's a symmetrical molecule. Since this is sp2 and sp3, and there's an observed inverse isotope effect, this is the rate determining step for that reaction. This, of course, is not the product. The product is here, where there is an isomerization from the cis to the trans. So all that's needed is, in a fast step, see how we can get back the trans geometry. What that requires is a rotation around this bond. Of course, as you can imagine, that's fast to give this. And of course, we have an elimination of H to give back our HSCN. So this is really a catalyst for the isomerization here. So this is actually fast, and this is fast. And the first step is rate determining because it goes from an sp2 to an sp3, and it's an inverse. Okay, so that ends this lecture for the kinetic isotope effect studies on molecules. So for this lecture, let's just do a quick summary. So the first is that the kinetic isotope effect studies are very important and useful in determining reaction mechanisms, specifically the rate determining step. So from here on out, whenever you propose a mechanism, you will be asked to indicate the rate determining step. The rate determining step can be determined from the kinetic isotope effect studies, or, as we have seen before, the rate determining step can be determined also from linear free energy relationship studies. Primary isotope effect involves the breakage of a bond. Notice here it's not necessarily a CH bond. That's the most common to study because of the magnitude, but it could involve a CC bond or any bond where there is an isotope bonded to another bond. Since we're talking about organic chemistry, it's typically to a carbon. So that's the primary kinetic isotope effect studies, and that determines the rate determining step where a bond is broken in that step. A secondary isotope effect involves the change in hybridization. So a normal secondary kinetic isotope effect studies involves the change of hybridization, in this case a carbon, from sp3 to sp2. This is known as a normal kinetic isotope effect. A change from an sp2 to an sp3 is known as an inverse. Why inverse? Because it's less than unity. And for the normal, it's greater than unity. Don't forget, these numbers are typically small. Typically small because it does not involve a bond breakage. It just involves a change in hybridization, which is reflected basically in the vibrational frequencies of the different bonds for the different intermediates. Here would be the sp3 or the sp2 carbon. And in conclusion, both primary and secondary kinetic isotope effect studies are very useful in determining the rate determining steps for different reactions. So I think that's the end of this lecture here. Yes, it is. So again, what we've covered so far are the tools that can be used, that typically used in research to determine the rate determining steps for different reaction mechanisms. What we'll do for the rest of the semester is we will apply these tools to study different reactions. For example, the elimination reaction, we'll go in a little more detail there. We'll look at substitution reactions and elimination reactions, etc. So once again, continue to study hard and refresh your memory on these different tools, because they will be used throughout for the rest of the semester. Okay? Continue to study hard.